So there we go. So you have heard before somebody talk about something being a strong acid, maybe, correct? Have you ever heard that term bandied about? Okay.
No, I didn't hear that.
So my guess is that those people, whomever were using that term, were probably using it incorrectly. Okay. So there are only 6 strong acids out in the world.
What are they?
Hydrochloric is one of them. Nitric. Hydroiodic. Hydrobromic. HClO.
Why did I put in the
1, 2, 3, 4, 5. I'm missing one.
I think you'd already started. Yeah. It's in somewhere in here.
Okay. What's the 4th one? Why am I forgetting? Oh, sulfuric. Yeah. H2SO4. Okay. So these are your 6 strong acids. So if they were not talking about one of these, they were incorrect. All right.
Okay, so we just automatically disregard their whole point if they were.
No.
Well,
but you realize in the back of your mind that, yeah, they're wrong. What they mean to say is that it is a concentrated acid. Okay? So you can have HCl that's very, very dilute. It is still a strong acid. Okay?
I'm going to be talking about strong acids all the time. I was thinking you were going to be on acid chips,
Even though she said you wanted to finish it, I still deleted that in my mind. I'm sorry. Okay. All right. So there is a difference between concentrated and strong. If it is not on this list, it is not strong.
Oh, it's weak.
But you can have, but you can have an acid, any of these that are different concentrations. And that's what I'm guessing the people were trying to say, that it was a very concentrated acid. Okay. So for example, this guy comes in at 12 molar when we get it here. That's a strong acid that's very concentrated. We could also dilute this down the same way that you diluted down like your copper sulfate, so that we could dilute it down and make it less concentrated. So what makes it strong versus weak? What a strong acid, I'm going to use this guy as an example. A strong acid is one that when we put it in water, so let me put this guy in water. It's going to completely break apart into the hydrogen. That hydrogen then will go with this guy and form H2 or H3O plus. And then what gets left behind? The Cl minus. Yep. Okay. Does that make sense? So every bit of this falls apart into these two things.
I have a question.
Yes.
Why doesn't that make Cl2?
Cl2? Oh, because it's going to stay as an ion. It's not gonna. Yeah, it doesn't. Yeah. So it's here. It's that charge. So it's going to remain that charge over here. Okay. It's not going to become a Brinkelhoff. It's not going to bond with another one of those.
Okay. Continue.
But the idea is that for every one of these are going to break apart, and it's not going to go back and reform any of this stuff. It's going to stay apart. Okay.
So we know that the hydrochloric acid is giving off its hydrogen because it's a strong acid?
Yes.
And then let's say you replace that with a concentrated acid, it would be the water in that scenario?
It's still going to break up. If this is your acid, you're still going to have, oh, you mean like if I do this, like H2O plus H2O?
Well, maybe I'm just misremembering.
Okay. So if I put this in, every bit of this is going to break apart and it's going to stay apart. So if you put water with water, if you just have water together, then that is considered, and this is kind of, water is kind of weird.
Well, I was just wondering if that was.
But you would get a few of these that come apart like this, and a few of these that come apart like this. Okay. Now, how many of those do you get? For water, your concentration of this, so, we were talking about this being 12 molar. When you have water, you get, at 25 degrees Celsius, you get 1 times 10 to the negative 7 molar for each of these. So very, very little of this is going to come apart into this. Like a stupid small amount. That makes sense? And that's actually how you get the 7 for your pH. So when you talk about water being neutral, being 7 for the pH, that's where they get it from, is because a little bit of that water will break apart into these. But so stupid small amount. I mean, that's just, if you take that and you break that out, that's the molarity. If you write that out of scientific notation. I mean, and that's just stupid. Right? All right. So these strong acids do not go in a reverse direction. And that's why we use an arrow that looks like this. It's a straight arrow.
It's not the weird.
Yeah. Okay, so that arrow goes like this. Now notice that when I drew this, I had this funky looking arrow. Okay. And what that means is that some of this stuff is going back this direction, and some of this stuff is going back this direction. Okay, and this is called something that is at equilibrium. Okay, and when we get into AP, we talk, do we talk about that so much more? Okay, so what classifies something as weak? Anything that's not strong is weak, and a weak acid partially ionizes, and I'll show you what that means in terms of an equation again here with an actual weak acid. So HF is a weak acid. Okay, now that doesn't mean that this isn't dangerous. Okay, small, very small concentrations of this, if you touch that, it will actually go through your skin and start like disintegrating your bone. Like this stuff is super dangerous. So just because it's a weak acid doesn't mean that it can't do damage. Okay. A weak acid can be very concentrated. It can eat holes through your clothes. It can, burn your skin. It can do all of it can blind you. It can do all of those things that are still dangerous, and you have to be careful with, especially if it's a concentrated acid. So there's a difference between a weak acid and a dilute acid. Does that make sense? Okay.
I got it.
So how does that look in equation form? You can quickly identify a weak acid in equation form because you will end up with an arrow that looks like this. Okay. Now, typically the arrow is kind of going like this, but typically when we write it, we do this guy just because it's faster. Okay. So this is a lot faster to write than, trying to pick up your pencil and doing all the other stuff. So this is typically, when you handwrite it, that's typically what you're going to see. Okay. So this is a weak acid. So we would end up with H3O plus because that hydrogen is going to grab a hold of this, and then you're going to end up with F minus. Very little of this is going to form. So let me see here.
So it still does the same, like.
Ka of HF. Yep.
So
So-
we should memorize the strong acid?
Yes, in AP you have to memorize your strong acids and you have to memorize your strong bases. The strong acids are the harder ones, but I will give you a couple hints. And the strong bases are easy, and I'll show you how easy they are in just a minute. Okay, so for the strong acids, 3 of them, so this one, and this one are your halogens. So those are the easy ones to kind of memorize. And then you only have these 2, these 3 that are left. So that's not too bad, right? And then the strong bases are easy. I'll show you those coming up.
The strong acids are easy.
All right. So getting back to this, if we look at these, this will, let me see.
On the first day of class next year, you have to ask them what the 6 strong acids are, because they're so easy.
Yeah. So this one probably isn't the best for this because this still has a decent molarity for this, for these guys, but the molarities of each of these will end up being this. So that's still a decent amount that kind of comes off, but it's still not enough to classify it as a weak acid. Yeah, it's still not good enough to classify it as a strong acid. And we'll talk about why and how you can figure all of that stuff out and all of that when you get into AP. Okay. All right. So the reaction will go to what's called equilibrium. Okay. And we know that it's in equilibrium because we see this backwards and forwards arrow here.
Okay.
The other ones go to completion. This goes to equilibrium. Both reactants and products are present in this situation with a weak acid. Okay, does that make sense? But more of this will be present than this stuff. Okay, so when we talk about a weak acid always has more of this stuff present than it has this stuff present.
Okay.
That's what makes it weak. All right. So strong acids, if we look at a strong acid, you're always going to have everything, and I'm just going to do the H3Os as H pluses, okay? You're going to have everything that's broken up into ions when you are in this format. Everything's going to be like that, okay? When you talk in terms of a weak acid, most of the stuff is going to be like this. And then you'll have a few of these that are floating around as ions. But most of it will be staying together in the weak form. You good? I think I have to sign your pass to get you back. On here, the answer I got was E, and there's no A here. The answer is not. Okay. I recognize that was an issue, and I'm like, it doesn't really matter because the answer is easy anyway. All right, so back to here. What does equilibrium mean to be at in a reaction? The pass? I don't think I got. I know, I can just write it. I need scratch. Do I need scratch paper?
Yeah.
Oh, did you do the back side of this? All right, I guess I don't need one. Okay. All right, so getting back. What does it mean for a reaction? The forward and reverse reactions are happening at the same time. Right. Okay.
The blank. Oh. the products and reactants are in a ratio that doesn't change.
Okay, yep, we can do that too. That's probably even better than forward and reverse reactions. Okay, so reactants and products are in a ratio that doesn't change. This does not necessarily mean that the reactants and products are in the same amount. They're not often. Most of the time they aren't. It's very rare that that happens. Okay. And like I said, I show you guys how to figure that out when you get into AP.
We have a fit? No. That's fine. We have a weekend to do it.
What? That is the best.
That's awesome.
It's not that bad.
Feel that. I
David,
like that.
Kleenex.
Most of these are just
Raylan?
labeling a thing.
No, just kidding, honey. It's just a joke. David's all spiffy today with a tie. All right. Did you guys have this page for notes?
We do.
Okay. You kind of broke up into conversation, so I was starting to wonder.
I'm just kidding with you. I was
All right.
like, you know.
That is a different arrow now. That's an equal sign with two dashes.
Oh, yeah.
That's
Right.
the same
So,
It's got two
like I
different-
said, when you type it, a lot of time, or when you handwrite it, it's this. When you type it, it often ends up being this
Is that
guy.
like the chemistry power rule?
I don't
What?
even know how to make that.
You get it.
This here, you just go, and then-
A two plus B two.
Like, is
Yeah,
that
that's
a
like
thing on the keyboard?
it's, you would have to find it in symbols. So if you go to insert and then symbols, you can find it over here in this.
So like only.
Um,
this can do it.
No.
Huh?
Because we won't define.
Well, you can do it in here. You could find it like online and copy it online and then paste it in.
Yeah, I'm sure it's part of
But
the-
it's hard to find those things. So, all right. So at the beginning of the reaction, all of this and all of this are forming this.
Cool.
Okay. And none of this is being formed. But as we approach equilibrium, I don't know what I was doing here for an example. I don't know what I was asking for here.
Okay, we
Um,
just cross it out.
Yeah, sure.
Yay!
So once the reaction is at equilibrium, both of these things are forming. So this is forming this, this is going back and doing this. So both of these reactions are running.
That looks stupid. I should have trusted.
All right. What classifies something as a strong base?
Like, yeah.
I got this one. Strong bases, ionized.
Twist! That's like good job, Gemma.
All the reactants turn to
Products. Oh, we got it.
and it doesn't go in the reverse direction. All right. So if we wanted to look at the example here, NaOH is a strong base. If we put that in with water, we are going to form Na plus OH minus. So this is all going to come apart in this water. Okay.
For real.
Yep. So how do we figure out our strong bases? So if we look at our periodic table, we have lithium, we have sodium, we have potassium, we have,
Video.
yep. So then we're going to kick over here. We're going to go calcium, we're going to go strontium, and we're going to go barium. Okay.
I like barium.
And yeah, this
too.
is
It's
cesium, and no, this is rubidium and then
okay.
cesium.
Then francium.
No.
Okay. So if this is magnesium, if you look at this, okay,
And then there's beryllium at the top.
yep. If you look at this, these three here, and then we kick over and we grab these three.
It's like a dude sitting
Okay.
down in the chair.
Okay. So we've got these that are going to make up our strong bases, and then you just have to add in your OH. Okay. Just remember that over here for these guys, these are +2 ions, so it's going to be OH2 for them. Because this guy is a +2 and this is a -1. So this is how you memorize your strong bases. So your 6 strong bases are LiOH, NaOH, KOH, CaOH2, SrOH2, and then BaOH2. So if it's not on that list,
It's not.
it's a weak
It's
base.
A weak base.
Yep.
Cool.
Okay. So those are your notes for today.
Chubbas, you got some new kicks.